Okay, good morning. We will today continue with the basic TTL and its operation and voltage transfer function. So I like to maybe talk about this a little bit to let you remember. The point was for making this kind of device was actually coming from DTL. So in DTL, there were these diodes, but some people noticed that, instead of putting these diodes this way, it is more convenient to put a transistor at the input stage. So, with the help of this, we can get a better voltage transfer function and also remove the charges here. Remember, base emitter charge when it's SAT, if we want to turn this off, the charge here can be removed also with the help of QI. So due to many advantages, this is preferred, and we, as we have seen in the previous course, if we give an input of 5 volts, this becomes reverse active, and then this goes to SAT. So output is going to be 0.2 volts. Therefore, we have an kind of inverter action. Half of it is justified here and verified. The other extreme was to give 0 volts. If we give 0 volts here, this junction would be turning on because of the current path here. So when that turns on, the transistor here, QI, can be either SAT or forward active. So we know that it cannot be forward active because forward active means there should be a current this direction, but this transistor prevents that. Therefore, the current there is going to be 0, and then QN is going to be off, and output voltage here would be 5 volts. So for 0 volt input, output would be 5 volts. So that's the other extreme case. And we noticed that the turning point from that condition, if this is 0.4 volt, this is the case, but if this is 0.5 volt, then an interesting state occurs. If that is 0.5 volts, this was still in SAT. So QI, we can say that still remains in SAT, and then remains in SAT, but then the current can be going in this direction. And then, the QN starts turning on. So that's the point. And then quickly, when the input becomes 0.6 volt, the QI remains in SAT, but QN goes to saturation also. So therefore, output voltage becomes 0.2 volts. Therefore, it switches. So the only thing that here is the transition from the SAT to reverse active position is not modeled very accurately. So this region is questionable region for the modeling. But in any case, this thing happens, and somewhere in between here, QI goes to reverse active. But finding that value, at which point the QI becomes reverse active, is going to depend on where you approach the question. Are you coming from this point or are you coming from this point? So that's not going to be accurate according to our modeling. So therefore, we don't even question that. is this become reverse active at 0.7 or 0.8? You know, we don't really care about that. So as long as we have our voltage transfer function like this, then everything is okay for us. Is that okay? So this was kind of repetition, what you know, I explained before. Now the thing here is we have other advantages due to the structure. And one of the advantage here is this removing this base charge. Base charge is removed much more faster than this condition. Even if we put a you know, resistor here and then remove that base emitter charge you know, accumulated during the saturation, this will give us a much larger current to remove that base charge. So the switching of QN will be very fast. So that's the you know, very important advantage of this TTL circuit. Okay, so we can even calculate that value, like how much is that current. So I discharge, let's start from here, maybe for the DTL case. For the DTL case, if we want to remove the charges here, so you know, this was originally at saturation, so VBE SAT was 0.8 volt. So the initial discharge, when the, let's say this voltage at the input goes from high to low, okay, when it goes to low, let's say it goes to 2.5 volt. It used to be, let's say, 5 volt. So when this happens, as you know, this point becomes 0.9 volt. Therefore, this becomes off. You know, so the current that will be used to change this voltage. So this is going to be 0.8 volts. That's the initial T0. So 0.8 volt minus VEE divided by RE is going to be our current. So we can give some, you know, various numbers here. Let's say this is this value, let's say, is minus 0.5 volt, okay? And then this RE, let's say, you know, extreme case. I mean, we don't want RE to be such a low voltage resistance, but if it is 1K, then this will be 1.3 milliamp, okay? So it is large current, instantaneous current. So this will be maybe switching from here to maybe smaller number, but the voltage swing that we want is it will be going from you know, VBE will go from 0.8 volt to 0.7. So when it reaches to 0.7, then it becomes off. So in that very short period, maybe the current will slightly change, but you know, it will be in this order. So it can be removed, that base charge. What about here? You know, here we need to look at, again, you know, going the voltage from 5 volts to 0.2 volts. So if this is 0.2 volts, you know, then we can calculate here when this becomes 0.2 volt here, this will be in saturation. So this will be in 0.8 and it will go to saturation, or actually it will go to forward active. Why? Why is it going to be forward active? Any idea? Let's say this is t is equal to 0. Okay, so that's the t0 point. Okay. So when t is equal to 0 plus, Qi becomes forward active. Why? Because this voltage is going to remain at 0.8 volt, and then there's a capacitance here, base charge, and base emitter capacitance. This voltage then is going to be 0.8 volt. So if this one is 0.8, this one is 0.2, then this voltage, we collector emitter voltage will be 0.6 volt, and 0.6 volt is larger than 0.2 volt. Therefore, Qi will be in forward active for a while, for a short while. So therefore, we can calculate that. Therefore, we can say that this is 0.7 volt, and then we can calculate this current in this direction. So that current is not coming from the transistor base, whatever normal operation, but it is coming from the capacitance in the base emitter. So therefore, that current is going to be beta F times IRB, and then that's the base current. And let's say this one is beta F times. How can we calculate that? That's going to be calculated from here, maybe VCC minus VBE on minus V collector emitter SAT divided by RB. Okay, so let's say RB is still 1 kilo ohm, and then this, I guess I made a mistake here. This is CC, right? So this is VCC. So this is 5 volts. This one is 0.7 volts. And then this VCE SAT. Is there a mistake here? No, this is input. VCE SAT of the previous stage. Oops. So this is V in effect from previous stage. So therefore, this voltage is going to be assumed to be 0.2 volt. And then let's say beta is about 100 forward. So then this is going to be about 410 milliamp according to my notes here. Okay. So very large. So Qn becomes off very quickly because the base emitter charge is removed very quickly. Okay. So that explains another advantage of this TTL structure. So this basic structure is good in a sense because of these effects, but it should be noticed that this break time is so slow, and then there are some other problems here. So it is better to put maybe one more stage between that input and output, and then therefore we can make this performance even better. So in order to achieve that, people came up with such a structure. So this stage is kind of inserted in between, and that's the splitter, I guess, is called. So therefore the transistor is called QS. And now this is going to, in fact, give us a nicer voltage transfer function. And this was used a lot in the past. Okay, so for the BJT type of devices, this became the most popular gate structure. So since we already analyzed the parts of the circuits partially, I guess it will be easier for us to understand the operation for the extreme cases. And then, you know, we can look at the values that creates this. Okay, so in the operation, we will be going back and forth to see how this is operating. Okay, so we will look at the extreme case where the input is 0 first. Okay, let's look at the case where the input is 0. In fact, 0 or 0 to 0.5 volt, but let's start with the 0. So when input is 0, I guess now we know the kind of the response of this input transistor. So this response is going to be, this QI is going to be in saturation. Okay, so when this is in saturation, why is it in saturation? We discussed this because this is going to be on. This junction is on. When this junction is on, again, it cannot draw any current here. So the current here is going to be 0. So this current is going to be 0. Therefore, transistor is in SAT. Okay, so we justified that before. So when this is in saturation, the voltage here is going to be 0.2 volt because of this voltage, 0.2 volt. And then this is going to be off. And since this is off, no current is coming here. This cannot turn on. And then this diode cannot turn on in this direction also. So therefore, it cannot be in reverse active either. So this is going to be also off. So when this is off, what happens? Then we have only a current path through here. But this current path is going to be, let's say, there is an, next stage Rn. And let's say this Rn is very large resistance, okay? Very large resistance. So if that's very large resistance, there is a current path here. So this junction can, even there's a leakage current here, IS maybe, this is going to be turning on. So this will be 0.7 volts. This will be 0.7 volts. And then the current here is so small that this will be about 0 volt. So V out can be calculated to be VCC minus that VRC minus VBE of P minus VD of on voltage, VDE. So the voltage there is going to be 5 volt minus 0 volt minus 0.7 volt and minus 0.7 volt. So therefore, V out is going to be 3.4 volt. So V out is this voltage. And then this voltage, therefore, is going to be V output high. Is that okay? So let me go to here and then say this, sorry, this is 3.6 volt, sorry, 3.6 volt. So this
Hocam,
will
bir şey
be
sorabilir miyim?
3.6. Sure.
RC'nin üzerinden geçen akım neden 0 oldu? Onu tam anlamadım. Orada volt niye 0 yani?
Now this is the critical thing is this. You know, there's going to be R load here. Okay, so this R load is about infinity, but not that infinity. So you know, but there's going to be a slight current. You know that, you know, when we have transistors or other things here, there's going to be small current here. So the small current is about 0 volt, 0 amp. Okay, so that current, we don't say that, you know, this DL is off and then QP is off. In practice, you know, if there was a capacitance here, you know, for the input, that can be charged up to the point where no current can be charged anymore. Okay, so if there might be a load capacitance here, C load also. So you know, the thing here is that that node will be charged up to 3.6 volts. Why? Because the current will be almost 0 when it reaches to 3.6. So when the current reaches to 3.6, this DL, you know, is going to be at the edge of turning on 0.7 volt, and then this junction will be at the edge of 0.7, and the current that is bringing them at the edge of turn off or turn on is coming from here, but that current is so negligible, so small. Therefore, here the voltage across RC is going to be 0 volt. Therefore, this voltage is going to be 5 volt. So when this is 5, this is 0.7, this is 0.7, the output becomes 3.6.
Tamam hocam, teşekkür ederim.
Sure. So yeah, that point is a little bit, I mean, maybe it will take time for you to digest. This is first time that you hear about it, but I guess you will understand that. So I could, you know, start the circuit like this. You know, if I had a circuit like this, and then, you know, this was the circuit, and the initial condition, and then there was this capacitance, let's say here, okay, CL. So what would happen to the circuit at the steady state? VCC, RC, and RCP, and then QP, okay? So let's say CL, VCL initially at 0 plus, it was, you know, 0.2 or whatever. Let's say, you know, it was 0.2, but 0.2 is very big extreme. So the state of the QP is questionable there. Let's say it was 3 volt, okay? So what will happen to CL at infinity? If you look at this, you know, capacitor will charge until this current through the capacitor becomes 0. So this will be charged up to, transistor will be in forward active, diode will be on, up to the point VCL at 0 is going to be 3.6 volts. So another way of seeing this. Is that okay? I hope it will be okay. So what is the, you know, at that critical point here, this is going to be on or off. So that's the edge. And QP is going to be somewhere between forward active or off. Okay. So that's kind of the edge. And this thing will be this output will be valid until, or valid for V in 0 volt, between 0 volt and 0.5 volt. You know, if the you know, 0.4 volt, for example, if this is 0.4, maybe I should do it with this one. 0.4, everything the same. This will be 0.6 volt, this will be off again, and this will be off again. Okay. However, for output, when it reaches to, let's say 0.5 here, then this will be 0.7 volt. And here, that 0.7 volt starts turning this on, becomes on, but still the current is 0. Because that's the edge, okay? 0 amp. But when this becomes 0. Let's say 6, then, you know, when this becomes 0. Let's go to this one, 0.6, and this becomes 0.8, this becomes still 0.7, and then you will have 0.1 volt here. So therefore, there will be a current here, and this is going to be 0.1, I mean, divided by RD, current. Okay, so that's the voltage, times alpha, because that's the emitter current. And since this is still 0.1, this is still off. Okay, but due to this, there will be a voltage drop here. So therefore, V out is going to be equal to 5 minus RC times IRC minus 0.7 minus 0.7 volt. So output is going to be 3.6 volt minus RC times IRC. What about IRC? What is IRC? IRC is, in fact, alpha times IRC is equal to alpha times IRD. What is IRD? What is IRD?
0.1 over
Yeah.
RD.
Yes, 0.1 divided by RD. Okay, so but you know, the point here, the critical thing here is that this voltage will remain here, okay, until what? What was the input? Nothing changes. 0.5 volt, right? When this was 0.5, nothing was changing, but after 0.5, output starts changing. So this way we can determine the input low. And then after this, the voltage will start dropping. Maybe here, let's do it this way. Okay, so initially it was this way. And then, you know, it becomes like this. So there will be another breakpoint or transition. What happens when is there another point? The voltage starts changing. This is, yeah, I mean, I could just write all these cases here. This is 0.6 volts, and this becomes SAT still, and then this is going to be 0.8 volts. So this will be in forward active, and then this will be 0.1 volt, and this will be off, and then this is VRC, and since this is in forward active, this current is IE, and then this will be alpha times IE, and this is between edge of cutoff, still off, or forward active. We call it edge of C, cutoff, or conduction, edge of conduction. This is edge of conduction. Okay, and therefore output voltage will be, Vout will be VCC minus VRC minus VBE of QP on minus V diode of L, which is on. Okay, therefore this will be, you know, 5 volt minus VRC minus 0.7 minus 0.7. So this VRC is in fact, you know, depends on the current here. That current is going to be depending on the input voltage. So VRC will be equal to RC times alpha times IE, and IE is IE. I can write everything at once. How can we find IE? That is V in plus 0.2 volt minus 0.7 volt divided by RD. Okay, so this is going to be IE. Is that okay? So as you noticed here, VRC is a part of Vout. Therefore, your output voltage will be depending on input. So due to the slope here, due to this minus sign, slope is going to be negative. And that's what we see here. Slope is negative and output is decreasing. Does it make sense?
Yes.
Okay. So another critical point here is what? When we increase Vin, you know, this voltage is dropping output. So, you know, maybe we can write the states here of the transistors. You know, in number one, this is the number one case. Number one case. Here, the transistors QI was SAT, QS was off, and then QO is off, and then QP, edge of conduction, so it's between off and forward active, off, and then DL is again edge of conduction, which is between on or off. So the voltage wise, it is 0.7, but no current is passing or very small current is passing. So, you know, we say it's kind of edge of conduction. So for this group, for this region, the transistor QI is still SAT. QS is forward active, QO is off, QP and DL as edge of conduction. Okay. So if we keep increasing, so let's say this is the second case. Okay, if we keep increasing that voltage, input voltage, for the third case, what happens? I mean, another critical point is when QO starts turning on. Okay, we said that this is, let's say, 0.6. This is in saturation. And this voltage is 0.8. So this is 0.7. And then the voltage here is 0.1 volt. Okay, and this is off. And this was in forward active. Okay, so that's the that was the case. But if we keep increasing the voltage here, let's say to 0.6, this becomes 0.2. So the other extreme is really when this becomes the input becomes 1.2 volt. When this becomes 1.2 volt, this will be still in SAT. And then this becomes 0. or 1.4 volts. The voltage here is going to be now 0.7, but this voltage will become 0.7 again. So that voltage becomes 0.7, then QO starts turning on. Okay. So what happens if it starts turning on? Then there's going to be this collector current. And that collector current is going to be coming from here, collector of O. And there's going to be current coming from here. This was edge of on anyway. So this is forward active. So this one is on. And then this current is going to be I collector of O divided by beta F of P transistor. Then there will be not only current coming from here through RC, but current coming from here. So more current will be flown from RC. So more voltage drop will be across this VRC. Okay. So therefore, the current or the output voltage becomes, gets lower, much faster rate. So for this case, V out is going to be still VCC minus VRC minus 0.7 volt minus 0.7 volt. So this VRC increase rate increases. Increase rate gets larger. Okay, so therefore we see another breakpoint here. So this point is 1.2 volts. So when this gets the slope becomes maybe sharper. And then, it will be dropping. We will notice this until 0.2 volts. 0.2 volts. So that's the third case. For the third case, again, QI is SAT. Again, QS is in forward active, and then QO is forward active, and QP is forward active. QO, we don't know about this one, but yeah, it should be that way. Okay, and then QO or DL is also on. 2, 3, 4, 5, 2, 5, yeah, 5 elements, 5 values. So is it clear why the slope becomes larger?
Yes.
Because QO turned on. Okay. So maybe I can erase this. Oops. Okay, forget it. Then what happens? when does this, point? Maybe I should select a different color here. I don't know which color to select. Blue. Okay, so what is this case? Let's say this is the fourth. That's 1, 2, 3. Okay, so this gets larger. Viot drops faster until QO becomes SAT. Okay, so that's the fourth case. So this is the fourth case. Is actually the transition point, is the fourth case. So we will be, let's put the numbers here. What happens? When does this go to SAT? In fact, when this goes to SAT, this is 0.8 volt. And interestingly enough, when this becomes SAT, when this becomes at 0.8 volts, this also becomes SAT. I mean, going both of the QS and QO to SAT is very sharp. Okay, so this becomes SAT 0.8, and this is going to be SAT at that point. So this will be 0.2 volt. So therefore, the input that creates this is going to be 1.4 volt. So when this is 1.4 volt, this is the case it becomes. And why do we say also this is the SAT voltage? And this is 0.8, and this is SAT. That means this is 0.2 volt. That means this voltage is going to be 1 volt. And then this is output is going to be 0.2 volt. And 1 volt and 0.2 volt cannot turn on this junction anymore, DL. So this becomes off, and this becomes off. That's the reason why we put this DL here, basically. So in order to be able to make QP off.
Hocam son kısmı tekrar edebilir misiniz acaba?
Sure. So we say that when this is SAT 0.8 volt, this is SAT 0.2 volt, so this becomes 1. So for this case, we want to be able to turn off the QP, and in order to do that, that's the reason why we put this DL. Okay, so 1 volt and 0.2 volt, 1 volt, 0.2 volt, 1 volt is not enough to turn on both QP and DL. Okay, so QO is SAT, therefore VBE of O is equal to 0.8 volt. QS is SAT, so the collector emitter of splitter transistor is 0.2 volt. So therefore the collector of splitter transistor is equal to 1 volt, and then V out is 0.2 volt. So the voltage between V collector splitter minus V out is equal to 0.8 volt. Not enough to keep QP and DL off. For on. Okay, since it cannot keep both of them on, therefore they are off. QP and DL becomes off. Okay, so I think we should start giving a break soon, but that's the that's why this voltage becomes 0.2, and this SAT means what? Beta F times I base of O should be larger than I collector of O. Okay, so I collector of O, I'm claiming that it is 0 amp, but it is satisfying this. So it is consistent, everything is consistent. Questions? Any question?
Hocam 1.2 ile 1.4 arasında bir input değeri verdiğimizde nasıl olacak? Yani structure nasıl olacak? Ben onu anlayamadım. Hani düşüş olacağını düşünüyorum ama.
So that's the something that the transistors are going to be in transition mode. That's why that's actually it's very tricky, so we don't go to that value. So as I told you, if we start questioning here the values, like for those kind of cases, so your question is 1.3 volt. Okay, what happens? So this will be still 1.5 volts, but then this is going to be going from forward active to saturation. Initially it was forward active, both of them were forward active. So maybe this is going to be 0.75, and then this will be 0.75. So, but we don't have that in our models. We don't have that. We say that it goes directly from forward active to SAT. It jumps, and then when it jumps from forward active to SAT, the voltage becomes 0.7 to 0.8. So so we don't question that, but we know that transistor transition is happening there, and the voltage between base emitter voltage goes from 0.7 to 0.8. So this is similar to the case where we analyzed in DTL, right? Transistor was directly going from off mode to SAT mode. So that's why let's not talk about this. And then we know that the trend, and here the transistor, we say it goes from forward active, in that transition point, but with forward active with large currents, QS and QP, we say forward active, but with large currents. So the voltage, base emitter voltages goes from 0.7 volt to larger voltages. Okay.
Tamamdır hocam. Teşekkürler.
Okay. So this voltage we already determined, and that voltage is going to be finally 1.4 volts. Okay. So therefore we call this thing V input high. So we already determined V output low. We know output high. We know this. We know this. So there's only maybe this voltage. So we can say we input break voltage. This one is the only unknown in our current graph. We output breakpoint. So other than that, we already obtained voltage transfer characteristic. How can we calculate this? We output breakpoint. We can find here the edge of transitions here. So approaching from here, we can find VOB. At which point this break occurred? When the transistor was, QS was forward active, QO was off, and then this was edge of whatever. Okay, so that's the thing that we will be finding. Maybe I should give a break of 10 minutes. Is that okay?
Yes.
Var mı soru? Okay, dear friends, let's continue for this standard TTL voltage graphic. So do you have any questions after these explanations? Now, this region is not really determined in our transistor modeling.
Hocam, are you sharing the screen now?
Sorry, I'm not. Probably. Okay. So do you see it now?
Yes.
Okay. So this region is a transition point, and then for QS and QO to go from forward active to SAT. Okay, here QO and QS starts from forward active to SAT. Okay, and in all these regions, now this will be the region where QI is going to be SAT, QS and QO becomes SAT, and then QP and DL, DL becomes off. Okay, so that's the states of the transistor, and after a while, QI becomes reverse active. If we keep increasing Vn, QI becomes reverse active. But again, finding that exact point is not going to be possible, because SAT to reverse active, remember, SAT to reverse active model was here. You know, this was the representation. In fact, the real thing is like, you know, it comes like this, and then it goes like this. Okay. So this was V collector emitter, V collector emitter, and then IC graph. So this region is not really very clear. Therefore, we don't really care, you know, when this QI becomes reverse active. But if we go to extreme, if we apply 5 volt to V in, it's clear that when we apply 5 volts to here, it's clear that this will be on, but this will be off. Okay. So therefore, it will switch to reverse active at the extreme case. Questions? So the only point was in that graph was this QOB. How can we find that QOB? QOB me find that value. I guess QOB, maybe I can determine it here. QOB is the point where QOB is the point where QS QO also becomes forward active. So QS is forward active. QS is forward active. This one is forward active. And then QO is off. But here the only difference is QS is forward active. QO becomes forward active also. So that's the transition point. You know, from here to here, VOB is the point where QO starts turning on. That means to forward active. Okay, so that's the critical point. So QO was off. It becomes so at that point we know that the current that is drawn from here, and this is the current, I mean the voltage becomes 0.7 volt here, but the current that comes through here is 0 still, 0 amp and 0 amp, because when the current starts increasing, that's the next area, next line. So therefore at this point we know that V base to emitter of O is equal to 0.7 volts. But still I collector O and I base of O is 0. So VB of O 0.7 means we can find V RC. Okay, so VRD is 0.7 volts. From here, VRD divided by RD is going to give us the current, which is the emitter current of the splitter transistor. And then that emitter current of the splitter transistor times alpha, okay, alpha times IES is going to give us I collector of S. I collector of S is also equal to I RC, because you know, this current is 0, so this current is still 0. IB of P is also 0. So you know, from here I can find output voltage. So V out for this case is going to be equal to VCC minus 0.7 minus 0.7 minus VRC, and the VRC is equal to RC times IRC, okay, IRC. And what was IRC? IRC was this, and then what was this? This was this, okay? So that depends on the resistance values, RD and RC. But that's how this value of V out is called VOB. Is that clear? Are you lost? Are you still with me?
Yes.
We are with you.
You are with me. Okay. Yes, you are with me. Or yes, you are lost.
Bitiyor hocam.
Okay. So, you know, this, I guess there are a lot of examples in the last year's questions also, and we'll be giving you maybe a homework also. So the good thing here is that, you know, all the transistor states and whatever is repeatable here. So once you understand the concept, you know, determining the transistor states or diode states are here not going to be complicated anymore, because you know that when input is 0, QI becomes SAT. Why? Because, you know, collector cannot have, or the base cannot have negative current, therefore QI, collector current, is going to be 0, so that means QI is SAT. So when it's SAT, the voltage and the base is going to be, you know, 0. Let's say 2 volt, and then QS is off, Q is off, and then QP and DL are at the edge of conduction, and then output is going to be 5 minus 0.7 minus 0.7 minus 0 VRC. So and the transitions are very clear, so you will know this, and you can solve this very quickly. Maybe it will take time, you know, to calculate the current values and voltage values. But one other trick is that, you know, in order to find those transition points, we already calculated some of the currents. And so if you need to calculate it again, then it will be not that complicated. Or you can use the value before. So, you know, after this, of course, we need to find maybe and calculate the fan out. So the fan out will assume the next gate is a similar gate. So the next gate is similar. So input, we will be calculating this for output high case and output low case. So for output low case is when input is high voltage. So output is here. Output low case. Let's calculate this one first. In order to get output low, input should be what?
High.
Yes. So let's say input is 5 volts. Okay. We already analyzed the transistor states. We know that this junction cannot be on. So this is off. So this junction should be on because there's a current path here. Okay. So therefore, base, the collector is on, means the transistor QI is in reverse active. And the voltage here is going to be in reverse active 0.7 volts. So, since there's a current here, we assume that current is large enough to put QS into SAT. And then this is supposed to be also remain in SAT. So this should remain in SAT. So here, beta forward times IBO should be larger than I collector of O. So that's the condition. And then output is going to be 0.2 volts. So initially, if this one, ICO is coming from two sources. Maybe coming from here or coming from next stage. So if nothing is coming from the next stage, if n is equal to 0, ICO would be 0. So coming from here, let's call this thing I don't know what, maybe IDL, okay? IDL plus n times I in prime. So what is the state of IDL? So we say that this is going to be SAT 0.8. So this will be in SAT 0.2. So this will be 1 volt. So this will be off. And this will be off. Therefore, this will be equal to 0. So the condition, the maximum N, can be found from here. Beta FIBO is larger than N times I in prime. Is that okay? So we need to determine IBO and we need to determine I in prime. The current coming from here is going to be called I in prime. Okay, so those are the two things we need to find. Output low case. So it's also easy to find that value for the output low case. So let's say this is 5 volts. This is reverse active. So this is 0.7. Okay, this is 0.8. 0.8. Okay. So the state of this is SAT. This is 1 volt. And then these are off. This is off. Since this is in saturation, this is 0.2 volt. Since this is 0.2 volt, this junction is on. And this is going to be 0.8 volt because this transistor will be in SAT. And then this is going to be off. It's going to be off. Output here is going to be 3.6 volt. Okay, so low output and high output here. And that's it. Okay, we can determine this IN prime. IN prime, that's going to be equal to 5 minus 0.2 minus 0.8 volt divided by RBX. You know, this one is I base of input X, I base of input X. Since it's SAT plus I collector of input X, but this is 0. This whole thing is going to be equal to I emitter of IX. So I emitter of IX is going to be equal to IM prime. Is that clear? Okay. So we also need to calculate this current. Let's choose another color. This current. I base of O. Why? Because I base of O times beta F should be larger than I collector of O. What is I collector of O? N times IM prime. Okay. Why do we need this? To keep QO in SAT. So if we keep, you know, putting more gates here, more gates, that current is going to be increased, and then this value cannot be satisfied. Okay. So here IBO needs to be calculated. And how can we calculate IBO? IBO is this current minus this current. Okay, so IBO is I emitter of splitter minus 0.8 volt divided by RD, because this is IRD. Okay, so in order to find that, the only unknown is this IES. So what is IES? You know, since QS is in saturation, okay, this one is question. Let's do this. IES is equal to IB of S plus IC of S. So we need to calculate this current and then add them, because this is in saturation, not in forward active. In forward active, beta times I base would give us emitter current. But here, they are coming from different, you know, sources. So IBS is going to come from reverse active device. ICS will come from up. So ICS is, I collector of S. I collector of S is very easy to find because this voltage, we know it's 1 volt, and we know this is 5 volts. Therefore, it's very easy. This one is equal to 5 minus 1 volt divided by RC. What is this 1 volt? You know that. This is V collector emitter of splitter in SAT plus V base emitter of O in SAT. So this was 0.8 volt, this was 0.2 volt. Well, it's kind of repetition what I'm doing, but you know, just to make sure you understand it. So here, what is this one? IBS. IBS is this. IBS can be calculated considering that this is reverse active, QI. And you know that IBS is equal to this current. And so that current is in reverse active. This current is for QI. This is like acts like an emitter. Remember? So for reverse active, if I can find this current, IBI, and then multiply that with 1 plus beta R, that's going to be IBS. IBS is equal to, coming from QI, okay, from QI, it's equal to 1 plus beta R times IBI. Okay, so this is reverse active. In reverse active, this current is let's say this is whatever, you know, later on we will calculate this because we will need this for the other fan out case. But in any case, this will be beta R. This will be beta R times IBI. And this current is going to be 1 plus beta R times IBI. Okay. So beta R is given, but we need to find this one now. What is IBI? IBI is easy to determine. We need to find this voltage here, and this is 5 volts. So 0.8, 0.8, that means 1.6 plus 7, 2.3. So this voltage is 2.3 volts. So IBI is equal to 5 minus 0.8 minus 0.8 minus 0.7 divided by RB. So it will be 2.7 divided by RB. Okay, so that's it. We solved it. So you find this IBI from here. From IBI, you find IBS, and from IBS, you know this one. And then once you know this, you know that IBO can be calculated because of this. And then once you calculate IBO, you already know this, beta, whatever. Then beta is going to be calculated. Is that clear? And from here, Okay. I mean, I'm not solving a full example here, but this is how you obtain it. I mean, if you want, you can write all the equations at once and then find this n value. Let's do the output high case, and then we can, end the course today for today. So output high case means this is high. This is then should be low. Okay, low. So for low, we can say that this is 0.2 volts. If you want, you can say 0 volt, but 0.2 volt is a better value here. So if this is 0.2 volts, this transistor will be what? In SAT. So therefore, the voltage here is going to be 0.2. So this voltage will be 0.4 volt. And then this cannot turn on these two junctions off and off. And here, output will be high. And then, QP is edge of conduction. But when this is high, we know that it will be about 3.6 volts. Here, if nothing was connected. If something is connected, this Vout is going to be affected. So Vout will be 3.6 volt when n is equal to 0. Okay, but if that n is not 0, then that voltage is going to be high enough to put this transistor into reverse active. When this is reverse active, this will be in SAT, this will be in SAT. So this voltage will be 0.8 volt, this voltage will be 0.8 volt, this is reverse active, so this is going to be 0.7 volt, this was going to be 2.3 volts. Okay, so the current, this IN prime, can be calculated. This current IN prime is going to be equal to beta R times I R BX. Okay. So IN prime will be equal to beta R times IRBX. What is IRBX? Five minus 2.3 volts divided by RBX. This is reverse active. So beta R we don't know, but typically it is 1, 2, or sometimes they designed to be lower than 1 even. So the emitter is like reverse active, so it acts like a collector. So that's why BR times this is the case. Okay, so what is the effect of this? So we can have n times IN prime. So that current is this current. Okay, so I emitter of P transistor is going to be now n times IN prime. And if n is 0, that is 0. What about Vout? Vout voltage is going to be equal to VCC minus VRC minus 0.7 minus 0.7. So here, if n is equal to 0, VRC is equal to 0. But if it increases, then this will increase. So this VRC is the critical thing then. VRC is equal to RC times IRC. What is IRC? Here this was off. IRC is this one. IRC in fact is equal to I B of S. Sorry, IB of P. IB of P is equal to, because that's forward active, I E of P divided by beta plus 1. Beta forward plus 1. So what is EP? And we already calculated here, EP. So therefore, V out will be equal to VCC minus, oh my God, shall I write everything all merged together or no need? No need, because the time is finishing. But VRC, EAP, VRC, I can write it right away. N times IM prime divided by beta F plus 1 times RC minus 0.7 minus 0.7. Okay, so okay, so how can we find the fan out? The fan out will be limited by V out. If we say V out is equal to 3.6 volts, then fan out will be 0. But if we say V out can drop down to, let's say, due to the high noise margin, can drop to 3 volts. Okay. If V out is allowed to drop to 3 volts, then we can find about this, and then this voltage then should be 0.6 volt. So N times IM prime divided by beta F plus 1 volt times RC should be less than noise margin, so 0.6 volt. So this can be noise margin high. Oh, sorry, noise margin high is not correct, sorry. Sorry. So 1.4 volt, this voltage can be coming from 1.4 volt input high plus the noise margin, let's say 1.6 volt noise margin high. This is V input high voltage. So if we allow, if we don't have any noise margin limitation, then this can drop to 1.4 volt. But that's the extreme case. Typically, we have a noise margin determined, and then that's we find this voltage here, 0.6, and then that's what it is. Is that okay? And then here you will find a limit to n. So n max for high case can be calculated. Okay. So I'll stop here. Please go through the slides. I will share also, and the course. link. Tamam mıyız arkadaşlar?
Hocam benim bir sorum olacaktı.
Tabii.
Şimdi yarınki ders saatimizin bir tanesini kullanmıyoruz.